this problem we have the cost function. So this is the cost of manufacturing X items. They ask us, though, to minimize not the cost, but the average cost. So to find the average cost, you take the cost for all the items and divide it by the number of items that you made. That will be, we'll call that the average cost here. So in this case, if we take the cost and we divide by x, each term has one x in it. So we get x squared minus, we get x squared minus 20x plus 20,000. So we just want to optimize this function, the average cost. I can see that that's a parabola, and so we're just looking for the bottom of the parabola. That's going to be the only place where the derivative is 0. So let's find the derivative of the average cost with respect to x, which would be 2x minus 20, and set it equal to 0. Then 2x equals 20, so x equals 10. So we'll minimize our average cost if we make 10 items. So this is the production level. So x should be 10, so find the production level. The production level, we should make 10 items. That will minimize the average cost of making the items, the cost, the cost per item, basically. Let's see, this one's a little more general. Prove that the production level, if any, at which average cost is smallest is a level at which the average cost equals the marginal cost. So we have x, that's the number that we're making, that's the production level. And then we have the cost to make x. And then we could talk about the average cost. The average cost would be the cost to make x items divided by the number of items that you made. That would be the average cost of x. This thing they call the marginal cost, that's an economics word for the derivative. So the marginal cost of x is the derivative. The idea is that if you make a change in the number of items, then you would multiply that by the derivative, right, to get the change in the cost. Change in output is slope times change in input. So that would give you an estimate of what the derivative would give you an estimate of what the cost to make the next item is. So if you had a cost table where you had the number of items, 1, 2, 3, 4, 5, 6, and you had the costs, maybe 2, 3, 4, 5, 6, 7, then in the margin you could make your own table of how much to make the next item. Let's see, 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1. Looks like here the marginal cost is 1. It costs you $1 to make the next item. So they want to say, prove that the production level at which average cost is smallest is a level at which the average cost equals marginal cost. Okay, so they're basically saying we want to minimize the average cost. So, well, how would we minimize? We take the derivative, right? If you want to take the derivative of this quotient, the cost divided by the number of items, you take the derivative of the top times the bottom minus the top, which is the cost, times the derivative of the bottom, which is 1, all over the bottom squared. We want to figure out where's the critical point. So the only way this fraction could be 0 is if the numerator is 0, which would mean that c prime x minus c of x has to equal 0. And if we rewrite this, we could move the c of x over and divide by x. And what we have here is the derivative cost, that's the marginal cost. And on this side we have the cost divided by the number of items, that's the average cost. And so we have our critical point when the average cost equals the marginal cost. Yeah, that's what we were supposed to show. One more of these problems. We've got another cost function. X represents thousands of units. Is there a production level that minimizes average cost? If so, what is it? Well, we just showed that the minimum of the average cost is when the average cost equals the marginal cost. That's what we showed in the previous problem. So the average cost is the cost to build X items divided by the number of items which you built, which was x, in this case x thousand items, x thousand units, and the marginal cost would be the derivative of the cost, and the derivative of this would be 0 plus 96. The 3 halves comes down, and we'd have 6x to the 1/2. So we're just interested in seeing if we can solve this problem. If I multiply both sides by x, I have 96x plus 200 plus 96x plus 4x to the 3 halves equals 96x, and multiplying both sides by x, we get 96x. X times x to the 1/2 would be x to the 3 halves. Okay, there's a 96x on both sides. That's nice. If we bring this 4x to the 3 halves over and put it with this 6x to the 3 halves, we have 2x to the 3 halves. If we divide by 2, we have 100 equals x to the 3 halves. If I square both, I have x cubed equals 10,000. And finally, then I'd have x is the cube root of 10,000. So let's see. The cube root of 1,000, this is 1,000 times 10, and the cube root of 1,000 is 10. And so we have 10 root 10. That would be the production level that minimizes cost. That's the production level where the average cost is equal to the marginal cost. So we have 10 times root 10,000 thousand units, 1,000 items there. And that would be the production level that minimizes average cost. Now, do I know that that's a minimum? That's a good question. If there is a minimum, it should occur there. But how could we tell that it's a minimum? I guess one way we could have done it would have been to look at the average cost. So the average cost would be 200 times x to the minus 1 plus 96x divided by x would be 96 plus 4x to the 1/2. So we take the derivative of the average cost. We're trying to minimize average cost, so we take the derivative of the average cost. We get minus 200x to the negative 2 plus 2x to the negative 1/2. Now we take the second derivative, and the negative 2 comes down. We have 400x to the negative 3 minus x to the negative 3 halves. So let's look at our average cost when x is 10 root 10. So the second derivative at 10 root 10 is, let's see, we know x cubed is 10,000, so we have 400 over 10,000 minus, let's see, this is 1 over x cubed, x to the 3 halves, so that would be x cubed, that's 10,000, but take its square root here, and that would be 400 over 10,000. If I get a common denominator, I'd multiply this one time by the square root of 10,000, so we'd have 400 minus the square root of 10,000, all over that common denominator of 10,000. And the square root of 10,000 is 100 over 10,000, so we get 300 over 10,000. The important point is that's a positive number, which means if we look at the average cost at this point, right, it's concave up because the second derivative is positive at this location. So the function's concave up, so we do know that that's a minimum. Okay, so that production level minimizes cost.